Good afternoon, Sharks. Today we're going to introduce to you a solution that's going to change how people interact with technology, especially those with just one hand.
Sharks, today we're looking for a grade of 100% on our optimization project and $500,000 in exchange for 10% of our company.
Imagine you're a gamer, coder, overworked engineer, or someone with limited mobility. Conventional keyboards are based on antique typewriter designs, making them bulky, inefficient, and frankly, obsolete. Why type like it's 1873 when you can type like it's 2073? That's where we come in.
Modern keyboards were frustrating for students like us, so we sought to optimize the key locations and shape of a two-handed keyboard in order to make typing more efficient and more comfortable.
We present to you KEYBLAST, the one-handed keyboard for optimized speed, comfort, and productivity.
To guide the optimization, we started with a clear and measurable objective function. We used 30 design variables, one for each key. That included all 26 letters plus 4 punctuation marks to keep the scope manageable.
Realistically, the final keyboard would support macros, so each key could trigger multiple characters. And of course, more keys could be added later. This was just the foundation.
We organized those 30 keys into a single long vector. Each index in the vector represented a letter or punctuation mark, and the value at the index told us where it should go in the layout. Simple structure, but powerful for optimization.
Then came the layout itself. 2 columns of 4 keys assigned to the index, middle, and ring finger, and 2 columns of 3 keys designated for the pinky finger. Each finger started into the center of its zone, so we could measure how far we had to move to hit each key.
With the layout in place, we simulated typing by feeding in a string of characters and calculating the travel distance for each finger. Add those up and we get the total cost of typing that layout, or how much effort it really takes.
But we needed a real-world test case. So, we found a paper on the most commonly used letters and letter pairings in English. Using that data, we asked a highly advanced AI tool, ChatGPT, to generate a sample paragraph that mimicked typical English writing, perfect for our evaluating different layouts.
So now we had the problem framed, a way to measure performance, and real-world text to test with.
But here's the catch. We were staring down a design space of 30 factorial possible layouts. That's over a nonillion combinations, way too many to search by brute force.
So we needed something smarter, something that could explore a massive design space and evolve better solutions over time.
That's where the optimization magic comes in.
Genetic algorithms mimic natural selection. They evolve better solutions over time by combining the fittest results and occasionally introducing new ideas through mutation.
Here's how ours worked. For every key placement, we rolled the dice. Each gene in our keyboard DNA had a 40% chance of coming from parent 1, 40% chance of coming from parent 2, and a 20% chance of spontaneous mutation. This kept things fresh and exploratory without getting totally random.
We didn't just throw keys anywhere. We weighted the algorithm to avoid overusing weaker fingers like the pinky or ring, and to discourage using the same finger multiple times in a row. That way, our final layout wasn't just fast, it was comfortable.
And to keep things efficient, we introduced warm starts, saving the best layouts from previous generations and reusing them as parents. This gave us stability and consistency while still allowing room for innovation.
The result? A refined layout that balances speed, comfort, and accuracy, optimized through hundreds of iterations just like nature intended. Now, let's talk about the part that's just as important as performance, comfort. After all, you can have the fastest keyboard in the world, but if it's not comfortable, it's not going to last.
We started with 3 distinct keyboard geometries, each with 3 different arc radii. That gave us 9 design variations. But we didn't stop there. We took it to the people.
We hit the pavement, asking 30 participants to try each design and pretend to type on them. We wanted real feedback on comfort, not just theory.
The results were clear. The curved and mid-curved designs were by far the favorites, with only a small handful of users opting for the flat design.
With that feedback, we applied sequential quadratic programming to minimize the finger travel distance across the layout. This allowed us to refine the curvature while considering the impact on hand movement and ergonomics.
Once we'd optimized for comfort, we shifted our focus back to performance. We needed to make sure that the results actually made sense, so we ran some checks. Were frequently used letters close to the fingers? Check. No duplicate keys? Also check. Common letter pairs spread out for speed? Again, check.
As we continued running the genetic algorithm, we started to notice something interesting. Patterns began to emerge. Vowels clustered together on the stronger fingers. Rare letters got pushed to the sidelines, pinky and ring fingers, and punctuation banished to the corners.
Even though each generation gave us slightly different layouts, the trends were clear and smart. It wasn't just random, it was evolving toward a better design.
Eventually, we landed on a layout that captured those trends with the lowest overall typing cost.
Then came the final touch, layering in the ergonomics. By applying SQP to refine the arc curvature, we struck a balance between comfort and efficiency.
But here's the twist. You'd think flatter arcs would always win when it comes to reducing travel distance. And for 2 out of the 3 designs, that held true. But one arc surprised us. It hit a sweet spot balancing between distance and comfort better than the rest.
Sharks. Today we showed you how KeyBlast was born, from frustration to innovation to optimization.
We tackled outdated keyboard designs by creating a layout specifically for one-handed use, focusing on both speed and accessibility.
We built a custom objective function, ran thousands of genetic algorithm iterations, and engineered a solution that actually evolves to fit real-world needs.
And we didn't stop at function. We put comfort to the test with real users and applied optimization to the ergonomic form itself, refining the arc to fit the human hand.
KeyBlast. Typing evolved.
So Sharks, the only question left is,
Are you ready to take typing to the next level
With just one hand?
Make it 5% and you've got a deal.